let's talk about finding the common area between two polar curves. So we're going to find the common area between r equaling 3 sine of theta. So we'll call that r1, and r1, 3 sine of theta, is a circle around the y-axis with radius of 3. Diameter of 3, I should say. And then r2 is 2 minus sine of theta, and that is going to be this little limacon down here. It's just a flattened out circle. All right, so we want to find the common interior, so we want to find this area right here. So we need to find the boundary curves and make sure we know how to set up the integrals. We're going to use a calculator to do this, so I'm going to show you how to use your calculator to integrate polar curves. So remember that our angle lines always come out of the pole. So if I find my intersection points here, I always like to draw these lines from the intersection points down to the pole so we can see what curves we're doing. So if we look at it closely, right, there's two actually different areas here. So I'm going to get some more colors going, right? Below these lines to the black curve, right, we are using R1. We're using that 3 sine of theta as our R value. But in between them, I haven't used blue, okay. Right, the area in between them, though, the R value goes out to R2. So right here we have, this is an R1 radius. Right over here, like any point from that curve to the pole would be an R1 radius. I'll use green, I guess, for R2. Right, and all of our radial lines here from the pole out to that blue curve would use R2. So we're going to actually need 3 integrals for this curve. Now, because we have the graph, we can probably figure out what those angles are, but I'm going to just show you in case you don't have a graph, how do you find the intersection points? So, right, just like any other graph, right, if you need to find the intersection points between two curves, you're going to set them equal to each other. If I collect all my sines onto one side, I get 4 sine of theta equals 2. So sine of theta is going to equal 1/2. So that's going to tell me that theta could be pi over 6 or 5 pi over 6. Right? And if we tested these would in fact be these angles. Right? So if I do R1 of pi over 6, just to make sure, that's going to be 3 times sine of pi over 6. That's 3 times 1/2. That's 3.5. That's 3/2. I should say 1.5. So this is 3/2 comma pi over 6. And then it'll be the same thing over here for 5 pi over 6. So we also want to make sure that we know where the curve is starting. So if we test that to make sure, we have R1 of 0 is 3 times sine of 0, which is 0. Right, so that's over here. At this point, I guess I should use some different colors here. We'll use totally different color. We'll use red there. Right, so this is the point 0, 0, right? If I plug in 0, I get 0 out, and then I want to know how long it takes me to get all the way back around to the edge of the curve. So for a circle like this, all right, if I just want to test and make sure, I'll use, I don't know, green, right? R1 of pi over 2, just want to make sure I know where I'm at here and how the circle is moving. That'd be 3 times sine of pi over 2, so that's 3. So that's going to put me all the way out here. So 3 comma pi over 2. And then next time I'm going to get back to the pole of 0 is actually at pi. Right, so down here now I'm at pi comma 0. 0 comma pi for the angle. Right, so we actually only need pi to go all of these directions for the circle. So that means that our starting angle value is going to be 0 where the circle starts. We're going to split it off at pi over 6 when we split from the black circle to the blue limacon graph. We're going to split it again when we hit the intersection point at 5 pi over 6. So I guess I should label that over here. This is 3/2 comma 5 pi over 6. And then we're going to split it and end it at pi where the circle stops. So our total area, we're going to write this all out. We've got area is 1/2 from 0 to pi over 6. So that's using R1, so I'm going to do 3 sine of theta all squared d theta. So that is our first area right here. That was yellow on our graph. So we'll color that yellow, plus that middle section, 1/2, that's going to go from pi over 6 to 5 pi over 6. And that's our second graph, which is 2 minus sine of theta, and then all of that squared. Right, so there's our blue area, plus 1/2 times that final area. That's going to go from 5 pi over 6 to pi, where the black circle stops. And again, we're going to do 3 sine of theta all squared for that. So then we're just going to switch over to our calculators and type that all in. We're going to type it in very carefully. So what I'm going to do is I'm going to actually switch my calculator to polar mode for this. You don't have to. You could do it in x's. And then I'm going to go ahead and graph my two equations. So R1 was 3 sine of theta. I'm also just going to quick make sure I'm in radian mode, which I am. And then my second curve was 2 minus sine of theta. So I'm going to do that so that way I don't have to type the equations in each time and then properly square them. So I'm going to go to my home screen. I'm going to have 0.5, and then I want math 9 for an integral. I'm going from 0 to pi divided by 6. Right, pi is right over that exponent key. And then I want to square my first equation. So I'm going to do alpha trace, because that pulls up my list of equations, R1 squared. I'm doing it in terms of theta, and then I'm going to add 1/2, and my second integral was from, let's pull up my integral, I got pi over 6 to 5 pi over 6. And then I want to square my second equation, so alpha trace, option 2 for R2, square that in terms of theta, and then add my last integral in there. And again, I'm going from 5 pi over 6 to pi, and we want to square, so alpha trace, pull up my first equation, square it, put it in terms of theta, hit equals. Didn't take long to pop out there. So our approximate answer there is going to be that the area is about 1.872.